Right, guys, so we finally made it to the distinction, which is section 9, part 9. And we're looking at directing effects of electrophilic substitution. This bit's tough, I'm not going to lie to you. Don't know why it's here, but we do have some really difficult concepts to go through. I'm going to give you a lot of information in the video. It's going to require you guys to pause this and likely look up quite a lot of the things I'm saying. So brace yourself, this one is going to take quite a while. There are 4 main sections that we're going to be looking at in terms of directing groups and positions, and I've double checked the spec, and I think I can get away with you guys doing one set of examples for activating groups, one set of examples for deactivating groups. In the past, I've made everyone do all 4, so it takes a really long time. From this, what we're going to do is I'm going to assign you 2 benzene derivatives, and I'm just going to call it odds and evens. So when you get your sheet of lists, it's going to say odds and evens for distinction. If you're odds, you're going to be doing 1 and 3. If you're evens, you're going to be doing 2 and 4. They're only the sections that I'm interested in you looking at. So activating groups, you would just talk about methyl, and deactivating groups, you would just talk about nitro. Just like before when I gave you a selection though, you need to talk about all 4 before we actually go into it. Then we're going to talk about the directing groups of benzene to start off with. So what does this actually mean? I think directing groups is the first time I've mentioned this. I have mentioned the names para-substituted before, so you might have an idea of what this is, but I'm going to go into it a little bit more information now. Let's go. So this is the very general structure for a directing group of benzene. This is the general monosubstituted benzene derivative plus any general electrophile, and then we get what we call a disubstituted benzene. This is super general. This is equivalent to your R groups like before. The position that the electrophile is directed to, so where this is going to go, so typically 1, 2, 3, or 4, depends on the functional group that's already attached to the benzene ring. This functional group X can be one of 2 things typically. We can have it as an activating group, like a hydroxy or a methyl, or a deactivating group, like a nitro or a halogen, like a chloro. I'm going to go into a bit more information about what these mean a little bit later on, but the main section that I want you to take away from this bit is this here. So tell me about directing groups. I want you to tell me about the ortho, para, and meta overview and some brief explanation here. So what would actually cover this is essentially what I've just covered. So this reaction here with this diagram, so you can see here, ipso, ortho, meta, and para. Something that tells me where those positions are. Some brief explanation saying that the group attached to the benzene will direct the electrophile to a preferred position of ortho, meta, or para, depending on if this is activating or deactivating. Some type of summary like that is going to be good enough for me for this particular section 9.1. That could be about half a page. You have a diagram and have a look there. If you want to know more, I would have a look into searching directing groups of benzene, and then I would use the keywords ortho, meta, and para. You don't really see ipso very often, so don't worry too much about it. Well, ortho, para, ortho, meta, and para substituted. The next thing I'm going to talk about is the 4 main directors that you're going to be looking at. This is a section where you need to talk about all 4 of them, but I'm going to assign you 2 of them for the next sections. Here we have the 2 activating groups, and here we have 2 deactivating groups. And when I say groups, I'm talking about, let's do it in purple. I'm talking about this bit here. Oh, I don't like that. Let's go this one. I'm talking about this bit right here. So these are the activating or deactivating groups, respectively. For methylbenzene, we have a CH3 and an OH for phenol. Now, an activating group, so when you're putting this into your assignment, the way that I want you to talk about your activating groups is in the context of electron density. Now, let's go over here. I'm just going to focus on this bit over here. So for activating groups, we have like a hydroxy, an alcohol, or a methyl. This increases the electron density into the benzene ring, into this bit here. So it increases the amount the electrons are closer together within that ring. And this actually makes it highest in the ortho and para positions. So when you look at it here, it's going to mostly concentrate on these two areas. So we tend to get a mixture of 2 and 4 substituted when we use activating groups. So if we use an activating group of like a methyl or hydroxy, it's gonna make a product where the product reacts here or here, typically. Yeah, so that's how we get an ortho or para substituted. Now, when we look at deactivating groups, we see something very different. A deactivating group is an electron withdrawing group. So they pull electron density from that ring. So we've got a chlorine, and the chlorine super electronegative is going to pull the electron density out of there. And what that does is if the electron density is being pulled out of the middle, it means that this ring is less reactive. It makes it less reactive. However, the chlorine is only slightly electron withdrawing. So that still will direct some electrophiles to here and here, so 2 and 4. So ortho and para are still favoured with the deactivating group of a chlorobenzene. Which makes it quite simple for you guys. Now, the nitro group is extremely electron dense. So it's going to pull, it's extremely electron withdrawing. So it's going to pull almost all of the electron density. So if you imagine this ring here, it's going to pull all of the electron density right up to the top. So before, it's going to shift this maybe around here, probably around there. Whereas these ones before, they're going to kind of push it down a little bit. They're going to push the electron density down a little bit. So that would make this bit a bit more susceptible. And then once that's this bit more susceptible, and then eventually it goes over here, which makes this bit susceptible. So that's kind of how that's going to work. Now, over here with the nitro group, this is going to be really different. It's going to shift it right up here, which means we only get the meta-directed groups. So over here, this is now the only position for a meta. So it's going to be the position number 3. I think the ring moving was really, really poor. That was a really bad metaphor. But hopefully the words I use makes it a little bit clearer. And I would search up activating and deactivating groups if you want further explanation. I'm going to go into a little bit more detail about each one of these individually next. But I'm going to recap activating groups really, really quickly. So for activating groups, what they do is they increase electron density within the ring, makes it a bit more reactive, which means we're more likely to get 2 and 4 substitutions, 2 and 4, 2 and 4. Remember that this is 1. So that's going to be 2 and 4, 2 and 4, which is going to be ortho and para directing. When we look at deactivating groups, for chloro, for example, we have something that is now electron withdrawing. It makes it less reactive. However, 2 and 4 are still favoured. For a nitro group, however, it's extremely electron withdrawing. And that's going to direct most of our reactions to position number 3. So that's how we get nitrobenzene. For this, guys, you're going to have to talk about all 4. I don't want you to tell me about activating groups. I want you to tell me about deactivating groups. As you can see, I divided the page so that you can speak about it in the same way that I have. So you could do a page and a half. Information here with a reference. I'd use ChemGuide again for a reference. Or you can split the page in half, do activating groups at the top, deactivating at the bottom. I don't mind how you do that. Just make sure it works for you. Right, now let's get into some of the more individual examples. So I'm going to start off with this. This is something that we all need to do. So for activating groups, deactivating groups, we're now going to talk about 2 different types of conjugated models. One is this resonance structure, and this one's this resonating structure. We need them both. I'm giving you them both, so you just need to have them in your work. Whilst I'm doing that, I'm also going to talk to you guys about each particular directing group so you have some more information whilst I do this. So I'm going to leave this on screen. And again, just going back to hydroxy, what we know about it is it's a very activating group. It donates the electron density by something what we call electron conjugation. The lone pair of electrons on the oxygen. In the phenol, they donate it into the ring. So you can see here, it's got it forms a pi bond that pushes electron density down into the ring. The ortho and para positions are then electron rich. And you can see this by the curly arrows that I'm showing. So you can see here, there, look, there's that negative, and then the next stage, there's that negative. And that resonance structure will go around. If you remember this one, this is still position number 2, just flipped. And it rotates in that fashion. So this is ortho, ortho, para. And that is why they're directed to those points. So when I have an electrophile, which is positive, it's going to attack at this position. If it does it at that point in time, it'll form an ortho. If it does it at this point in time, it'll form a para. Remember that this is happening thousands of times in a fraction of a second. And whichever point that electrophile comes into contact, that electrophile comes into contact, bam, forms a reaction, then we get an ortho and para director. So I need this in here to show the hydroxy resonance structure. And you can have that below the activating groups if you want. Now the next one we're going to show you is a deactivating example. And this one is slightly different. I've actually removed one of them to make our lives a little bit easier for this one. So for nitro, what we're talking about for this is a very deactivating group. It's a withdrawal of electron density by conjugation. So it's the opposite of the one we just looked at. This one decreases the electron density in the benzene ring, whereas the other one increased it. The meta position is the least electron deficient, as you can see by the curly arrows that I've shown below. The electrons are mainly withdrawn from the ortho and the para positions, so the nitro groups in the benzene ring are extremely deactivating and very meta-directing. Remember, electrophiles are positive species, so they are not attracted to where you can see the positives on this. So if I was to draw an electrophile here for you, remember that the electron density within the ring is attracted to the positive. This is happening thousands of times in a second. This point here, and this point here is alternating between positives. So they're really, really not going to be attracted to that point. Now, if you look at where the most negative point is on this ring, at this moment in time, you can see the positives in this position here and this position here, if you jump between all three of these. Which means that these 2 points right here are always the most negative point on a ring. And this is position number 3. So every single time, at any point in time, you can see that position number 3, remember, if you go 1, 2, 3, or 1, 2, 3, it's symmetrical. At any point in time, this is the most electron dense. That's going to be attracted to the electrophile. It reacts. It is meta-directed. So it's going to form a bond in the meta position. Going back too much. There we go. So this is the resonance structure that we're going to be using, and the information about that is everything I've just covered. And I can do that really quickly again. So remember that nitro is a very deactivating group. It withdraws electron density by conjugation, just how I've shown here. That's what this resonance structure does. Meta is the least electron deficient, as you can see by those curly arrows. So the position number 3 is the least electron deficient. If it's positive, it's electron deficient. If it's not positive, it is not electron deficient. The electrons are withdrawn from the ortho and para positions. Nitro groups are very deactivating and very meta-directing. That's the short explanation I need for this bit here, as well as your nitro resonance structure. Right, I'll take a pause here and I'll get yourself a drink, get these sections done, and then we're going to talk about the next two, which are the types of reactions that we actually need. So, hopefully welcome back. Hopefully you had something to eat. What I've done is I've given you this flow chart for how to do your activating groups. Now, if you notice at the very, very start of the assignment, going back weeks now, if this loads, I don't think it's going to let me load it. It's not, is it? It's not. So what we're going to do is I'm just going to tell you guys, we're looking somewhere between, I think, 12, wait, 1, 2, 3, 4, 5, 8, add 4 is 12 to 16 reactions. It is a lot, but remember it's your distinction, and I've basically given you the formula for every single one. Now remember, you're only going to have to do 2 of these derivatives, not all 4 of them. If you had to do all 4 of them, you would have to do 8, 12, 16, 20, no, 8, 12, yeah, 8, 12, 16, 20. You have to do 20 reactions, but I'm not saying that. I'm saying you're going to have to do 12 to 16. Now, for those of you that have the nitro one, so if you are, I believe that is odds. It's been a long day. Is that odds? Yes, it is. Yeah, so if you are odds, you've been given the nitro group. Now, the nitro group only, like we just shown before, is meta directing. So you're only going to get meta products every single time. However, because of that, you actually have fewer to do than anyone else who has to do the other ones. So if you're doing evens, you have slightly more work to do. But if you're doing evens, your flowchart looks like this for every single one. If you're doing a nitro group, however, you have to work out what your meta products are. So you have slightly less to do in terms of quantity, but you have a slightly more difficult job to do because you now have to draw your own meta products. It's as simple as just moving it in the right position. Now, with a benzene derivative, you're going to have to show me the possible reactions with each of the electrophiles. So you're going to do, let's say, for example, benzene derivative 1 with a nitro group. What type of products can I get with that? Well, the methyl group, if we go back to methyl group is ortho and para directing, which means I might get, I'm going to zoom in. There's my methyl. I might get an ortho nitro group, so there's one product, or I could get a para nitro group, which is there. So there's 2 reactions for each electrophile, because you can have an ortho and a para. So you know what might should be good is if I do something like this. So I'll do this live. So a benzene derivative, let's start with this toluene. Going to add a nitro group to it. It's going to look like this. This is going to be your products example. Over here. I'm going to put this as an X, depending on what your derivative is. And it's an ortho position, so you're going to have your, I'm going to call it E, because this is your electrophile. You're going to have that there. Now, if you are part of the, your second reaction will then be a para substituted, which if I put it there, I'm not going to be able to fit it. I'll put it here. And sorry, my brain's crashing. There we go. And I have a para substituted one. So for you, for an example, there's one reaction for you. Your benzene derivative with the electrophile forms an ortho product. There's one line. And then you're going to have a benzene derivative with your electrophile and form a para product. If it is ortho and para directing, which 3 out of 4 of them are. If you have odds, you are also now doing the nitro directing groups. So this one. Nitro plus another nitro is only ever meta directing. So the only product that you have to draw for nitro is you have a nitro in the ipso position, and then it's meta directing, so the next one that you add on, your electrophile, is going to be in the meta position. And that is your answer. Now you need to replace your electrophile with every other electrophile. Remember that the charge does not exist in the product. There's no charge. There's the H+, so it does balance. There's no charge in your products. Right, this is a little bit more confusing, but I will explain more in class if we need to. The next thing I'm going to show you guys is a general flow chart for the ortho and para positions. For those of you that got meta, it's exactly like I've just shown. Your benzene derivative plus your group, and then that's going to be what your product looks like, because it's all meta directing, so it's all going to be in the meta position. So this would be NO2, NO2. This would be NO2 and a methyl group. This would be NO2 and a Br halogen. This would be NO2 and a SO3. And that's every single one of your products. For ortho and para, you need to do 2 reactions. 1, 2, and then you move on to the next one. CH3, 1, 2. Next one, Br, 1, 2. Next one, SO3, 1, 2. I would type these out and make sure they're subscripted correctly. Then you can just copy and paste them through, making sure you've changed them correctly. Double check that they're all correct. I'm going to get rid of this because I think it makes the notes look messy. But you have obviously my notes in the video. Yeah. The next thing I'm going to show you is a flowchart. So this is a flowchart of what those ortho and para would look like. As you can see, I've done all of the orthos and paras, so each one of yours will have 8 reactions, just like this. So for benzene derivative 1, you've got your ortho and para with nitro. Then you've got your ortho and para with a methyl. Ortho and para with SO3, and ortho and para with a bromine. And every single one of these is and would be correct. Some of you might be asking, can I draw it exactly like this? Yes, you can. You can't make any mistakes. So just make sure that when you are doing this, it all lines up and matches up. I would do this as 3 flowcharts. So there'd be 1. You've only got 2 actually to do. So I'll just do 1, and then I'll do another one with a different functional group in the middle. So a different benzene derivative in the middle. That's how I would do it. Or you could just do it as straight lines, 1, 2, 3, 4, 5. Make sure it's organized. Make sure each one is labeled so I know which is reacting with what. And then I can make sure that you're all correct. In terms of naming them, you don't need to name the products, thankfully. There's no mentioning of having to name the correct products of these reactions. However, I would identify if it's an ortho, para, or meta substituted product. And that's it. All right, guys, that's the end of 14B. It is an awful lot of work, but hopefully you should be able to get onto it. Good job.